Hi, everybody. Today's video is the first of our new textbook, our second textbook, I should say, and that's Applied Discrete Structures. So let's get started right now. Let's get started forthwith. So here we go. Oops, wrong one. There you go. Well, this is, let's just, it's very annoying having me in there. Let's just do that. Okay. Here we go. This is, let me make this on. Page 1. All right. So first of all, here's the this is the title. This is the book. Applied Discrete Structures. Again, it's a free ebook, just like the number theory book was, and it's by Ken Levasseur and with Al Dower, who is big part of this. And we're going to go through all this stuff right here. So, now we're not going to do all of these. There's a whole ton of stuff. I mean, there's enough in here for like 20 classes, 20 courses. I mean, what we're going to do, chapter 1 and chapter 2, and then we're going to skip from there. But let's just wait till let's just get going here. Itching to get going here. All right. So here we go. Set theory, chapter 1, set theory and set notation and relations. Well, first of all, I just want to say in general that set theory is one of the biggest, really, modern mathematics is really based on set theory. Really, set theory is a huge part of just the study of modern mathematics. Most things are put in terms of most mathematical theories really expressed in terms of sets. You may or may not realize that, but that's what it is. Even a function, if you will, a function is really, in a way, a set. How is a function a set? Well, we're going to learn. Anyway, well, I'll tell you right now how a function is a set. Let's go right here. So how is a function a set? Funny you should ask. Okay. So here we are, applied discrete. Applied discrete structures. So one of the things we're going to learn is when you have, well, first of all, I mean, a set is, a bunch of, a set is really an aggregate or a group or a collection of things, and we call those things elements of the set. Sometimes called members of the set, or elements of the set. So let's say I have a set A, and A is just A, comma B, comma C. So this set has 3 elements in it. And let's say I have another set, set B, and B is a set, oh, I don't know, 1, comma 2. Now you've thought of a function. Suppose we have a function from A to B, where f of A equals 1, and f of B equals 2, and f of C equals 1. Okay, so you could describe function f. So function f which goes from A to B, can be described as a subset of A cross B, which is the ordered pairs. So F is really, F is actually equal to, I'm going to make a subset now. 1, 2, 3. Okay, let's go commas in. A lot of commas. All right, so it's A1, B2, and C. So if I look at all of the ordered pairs, where A is my first got with the elements of A. That, by the way, how many ordered pairs are there? There are 6 ordered pairs. Let me just oops. Let me just make that clear. A cross B, that's equal to, let's make 6. 1, 2, 3, 4. 1, 2, 3, 4. Actually, you know what I'm gonna do? I'm gonna cheat a little bit. I'm gonna copy these 3. Give myself a little bit less work. And then maybe give me C, comma 2. This is A, comma 2, and that's B, comma 1. B, comma 1. So A cross B is a set of all ordered pairs with the left element, the left element is the guy on the left is from set A and the guy on the right is from set B. That's A cross B. And there are 6 of them. You have A1, A2, B1, B2, C1, C2. And this function F is actually a subset of A cross B. So I could describe a function as a subset of the set of ordered pairs. The truth is, any set that you've ever seen, let's say a real valued function, y f of x equals x squared. So you have 1 comma 1, 2 comma 4, 3 comma 9. I mean, there's all, so any set can really be described as any function can be described as a set of ordered pairs. Okay, actually, I don't want to. I don't want everything to bolded here. It's very bold. All right. Okay, moving on. Let's go back to the textbook here. We're gonna. Now, by the way, this first section is gonna be pretty wordy and a lot of stuff. There's a bunch of concepts, and hopefully, most of it will not be that hard. We enumerate a set usually with commas like this. The set of binary digits is 0, 1. The set of decimal digits is 0, 1, 2, ... 9. You can make any, we could give any name to this set and call it Bob, Ralph, whatever. And I notice it says B and D because B for binary, D for decimal. So often we'll name a set based on, that's just that doesn't matter. The 3 dots means you're going to skip a few, like let's say if you have the alphabet, so it's A, comma B, comma C, da da da. Because it's a pain writing out 26 letters. Or if, let's say you're listing numbers from 1 to 100. That's a big pain writing out all those numbers. So 1, 2, skip a few, 99, 100. Pal, there you go. That's what the dot 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 is for. Believe it or not, sorry about that, Elon. Believe it or not, believe it or not, it's pretty standard to write n for the set of natural numbers. Oh, natural numbers normally doesn't have a zero in it. I would not have the zero here. Then I would write w for the set of whole numbers when you do have the zero. But I don't know if that's a typo or if the author just is doing it differently. It doesn't really matter. I mean, what you call a set, it doesn't really matter. Z is used. I'm not sure why that is, but for some reason that's classically the case that Z represents a set of integers. I think because the word integer in German or something is also Z. I think Q represents a set of rational numbers. R represents a set of real numbers, and C represents a set of complex numbers. These are pretty standard, pretty routine. Because you don't use R for rational, you use R for real. Q for rational, and again, I don't really know where the Q came from. I don't know if maybe Q is quotient because rational numbers are really quotients, the fractions, Anyway, but another way I can describe a set is I could use what they call set builder notation. I can say Q is the set of all fractions A over B. That, by the way, that vertical line there means such that A and B are elements of the set of integers. So again, this little curve round E is an element of, and of course it means does not equal. So B cannot, because as you know, you can have zero on the bottom of a fraction. So in fact, I believe it says that here. A over B indicates the typical element of the set is a fraction. The vertical line, you say such that, or where A comma B is a way of saying A and B are integers. That little thing is element of. A comma in math are read as and. So A comma B means like A and B are both, So okay, now it is important to keep in mind. So basically, what kind of notation you use, whatever makes you happier. I know it's a weird thing to say, but notation shouldn't be something that just gets you bogged down. It should be something that makes it easy for you. So whatever you want to be longer or shorter, it doesn't matter. It's all good as long as it's good. A set is a finite. So let's look at here. Definition 1.1.1. A set is a finite set if it has a finite number of elements, and any set that is not finite is an infinite set. Who would have guessed that? Now, cardinality, that's an interesting term here. If A is a finite set, the number of different elements in A is called its cardinality. The cardinality of a finite set is denoted by what looks like kind of looks like absolute value signs. And it's interesting to use the word cardinality because why don't you just say the number of elements? Well, we're going to see that well, I don't know if we're going to get to it in this semester, but in this class, like I said, there's so many amazing things we can get to. That infinite sets have what's called cardinality, and shockingly, it was proven about a little over 100 years ago that different infinite sets have different, quote, cardinalities. So a very great mathematician named George Cantor, who was considered the father of modern set theory, proved that there are actually different levels of infinity. There are like bigger infinities, smaller infinities, and really quite amazing. In fact, he actually proved that there are infinite amount of different levels of infinity. Anyway, so let's continue. A subset. So if A is a subset of B, if and only if every element of A is also an element of B. And we write this symbol here, this little subset symbol. Now note, the subset symbol is not to be confused with the is an element of symbol. So here's some examples of subsets. If A is a set 3, 5, 8, and B is 5, 8, 3, 2, 6, then A is a subset of B because 3, 5, 8. Well, 3 is in B, 5 is in B, and 8 is in B. So everything that's in A is also in B. So that means, or you could say that B contains all the elements of A, so A is a subset of B. Now, the natural numbers is a subset of the integers, which is a subset of the rational numbers, which is a subset of the real numbers, which is a subset of the complex numbers. Notice that irrational numbers was left out of this because rational is not a subset of irrational. Actually, rational and irrational form, now that you know the word, the fancy words like partition, rational and irrational numbers form a partition of the real numbers. And let's see, if S is 358 and T is 538, then S is a subset of T and T is a subset of S because they're the same thing. Now, by the way, the order doesn't matter. See, here we write 358 and here they wrote 538. Doesn't matter. It's still the same set. It's the same set. Doesn't matter. I wanted to just mention something else. When we talk about cardinality, we said the number of different elements. So what do you mean different elements? So for example, so if I have 1, 2, 3, 4, 7, 9, 2, 5. So this set here has cardinality of, well, let's count. 1, 2, 3, 4, 5, 6, 7, 7. Because there are, I'm going to 7 different elements. And what are they? They're 1, 2, 3, 4, 5, 7, and 9. So this set has a cardinality of 7 because there's 7 different elements. In fact, really, when you write a set, you really should write it without the duplication. We usually don't put duplication in a set. So just saying. Anyway, okay. Again, so there's a lot. This first section just has a lot of definitions. So it's going to take us a little while. I might have to make 2 videos out of this because it's already getting pretty long. In fact, let me just. Yeah, actually, we're almost done. So I'm not going to make 1 video. Will cover everything. Set equality. Well, 2 sets are equal if they have all the same elements, basically. And another way of saying is that A is a subset of B and B is a subset of A. Means they have all the same elements. So there you go. Example 1.1.4. What was that? Oh, okay, yeah, right. This is an example 2 sets that are equal. And the number of times that an element appears in enumeration doesn't affect the set. So if A is 1, this is really the point I was making earlier. 1535 and 153 is the same thing. So A equals B. Okay. Yeah. And yeah, so there's some people have this thing called multi-set. We're not dealing with that. As far as I'm concerned, a set is a set and pow. And just a couple of things. If and only if is used in our definitions, and this is equivalent to saying, in other words, A if and only if B means A is equivalent to B, and meaning that these 2 concepts are the same thing. And occasionally we need to discuss the set that contains no elements, and we call that the empty set. And that's a set which contains no elements. So you usually write it either with this symbol here, or you just write it with 2 brackets, but nothing inside. And so A, now notice A is a subset of A, meaning any set is a subset of itself. And the empty set is really a subset of any set. So if A is non-empty, then A is called an improper subset of A. All of the other sets, including the empty set, are called proper subsets. It reminds me of like proper fractions and improper fractions. Um, anyway, and by the way, not everyone is in agreement with whether empty set is a proper subset, but it doesn't really matter. I mean, you know, you can argue, do I consider it? Do I not consider it? Everyone has to, as you know, mathematicians get very picky about little things. But then that's life. And that's it. That concludes our first section of our new textbook, our second textbook. Again, you have this. I did put this in Canvas for you, so you got access to it. Hope you really enjoyed this as much as I did. It was absolutely fabulous and wonderful. And we'll see you next time. Bye.